Okay, now what we are discussing is about growing a tree, and one would have this natural question that when do we stop growing a tree? How would an algorithm know when to stop growing a tree? Okay, and let me say that, okay, you start with a root node and you keep splitting if it's a binary tree into multiple splits, and it goes on until it reaches leaf nodes and fine. Okay, but when do you know that the leaf node has arrived? When does the algorithm know? This is something that the researcher or the analyst has control on. So there are so called control parameters, okay, and often in machine learning known as hyperparameters or control parameters, which we can use to control the growth of the tree. Okay. So for example, what is the minimum size to split? This is one hyperparameter or control parameter when you use an algorithm in a Python library. You can actually specify this, okay, and therefore suppose you specify that the minimum size to split is say 1000. Now a node will split only if the size is 1000 or more, otherwise it stops there, it becomes a leaf node. This is one control parameter. The other is when you split a node, minimum leaf size. Minimum leaf size is something that you can determine, you can control, that is a hyperparameter again. So when a node is split, what is the minimum size that a leaf node can have, okay, and if that minimum leaf node size cannot be achieved, then again that node will not split, okay, both are related, you can see, and therefore you can control the growth of a tree using hyperparameters like this, okay. Then there is also a concept of pruning. Again, you know, this relates to the metaphor of the tree, and therefore tree pruning, okay. How do you actually prune a tree? As soon as you hear the term pruning, you also get an idea that a tree is pruned once it is grown, okay, fine. But ideally there are two approaches to pruning a tree, or you know, shaping a tree and also controlling the size of the tree, okay. You may cut off some branches, okay, that is what typically done in tree pruning, right, you know, because they do not fit well, okay, into the tree, or they do not look well. Look is not the factor here, of course, but you know, it is the performance of the tree that matters, you know, as far as classifier is concerned. So there is a pre-pruning approach wherein you control the growth of the tree while the tree grows itself, okay, not control the growth, that term is different. You prune the tree while you grow the tree. Now a problem with controlling the growth or pruning the tree when it is growing is that decision tree algorithms are typically greedy algorithms, okay, and if you prune a tree very early in its growth, then what happens? Maybe you formed T1 is the root node, T2 and T3 are formed, okay. The algorithm will consider only this much, okay, for creating the split. It does not know in future if a split is made, a T6 and T7 will be formed and they will be very pure nodes. It does not know, it does not estimate that in advance while making the split. It is a greedy algorithm, and therefore obviously if you pre-prune, you may be losing potential future children who might be very pure, okay, which is not considered or accounted for when you make the split, and hence therefore since you can actually lose potential better trees in terms of purity, pre-pruning is not recommended, okay. Okay. Of course, you have control parameters as I just explained to you, which can be again used to control the growth of the tree, but if you control or prune too much, you lose potential future children. Okay. Now, post pruning approach is widely used, okay, because if you don't have a technique to prune a tree, the tree grows as big as it can, but you may not be able to explain. Okay. We have already learned explanatory analytics, we also learned predictive analytics. So, one application of a decision tree is to visualize the tree and to look at what is the structure, what are the rules, and those rules may be useful for decision makers. For example, we saw the rules that were extracted from the database of a bank some time back, and we also saw in our simple example what leads to sunburn, etc. So, the tree itself has certain power of visualization, certain usefulness in terms of application and understanding, okay, for decision makers, okay. And therefore, okay, in explanatory models, interpretability is an important aspect, okay. If the tree grows too large, how do you actually even understand the rules, because there are so many conditions which are looped together to form one rule, and then you get lost because it's too complex, okay, and therefore it is not useful for a decision maker, okay. The rules have to be interpretable, understandable and applicable, okay. And if the tree is too large, it's like building too flexible or too much non-linear models, okay. It is something similar, and therefore it is important to prune the tree and make it of size, reasonable size, okay. And also, similar to the bias versus variance discussion, in line with that, when your tree is too large, you have a problem, you potentially can have a problem of prediction performance also, okay. And you do not know which tree overall performs better, okay. It could be a smaller tree as compared to a large tree, okay. So, this can be tested out, okay, empirically, okay, using a post pruning approach called cost complexity pruning. And for cost complexity pruning, there is a cost complexity parameter or CCP, okay. This is known as CCP alpha, okay. T is the number of leaf nodes. Okay, it's a number of leaf nodes, and I explained the last two terms to you. Alpha CCP is a parameter which can be controlled by the researcher, okay. You can, if you are building a tree, you can actually input a value, say typically in an algorithm between 0 and 1, okay, and using that you can control the growth of the tree, okay. Not the growth of the tree, sorry, having grown the tree, you can prune the tree, okay, to be more precise, okay. You grew the tree into its fullest extent, and then you apply an alpha value to prune the tree, so that the tree becomes more ideal in terms of its overall performance. And how is that performance assessed? Well, this part of the formula actually is about the classification okay. Although this formula is applied to continuous valued, it looks like a regression exercise like yi minus y cap. So, this is not directly applied in a classification context. We have seen the formula for calculating classification error in a previous session, right. So, that is that is the method to calculate classification error, but the idea is to show that in a formula that on one side for every terminal, okay, there are t number of terminals, okay, for every terminal you calculate the classification error and you sum it up, and that therefore this part of the formula is the total classification error. So, to start with, when the tree is grown into the fullest extent. So suppose there is no term as an alpha, suppose you make alpha 0. So this term does not exist. So therefore you have a full tree grown and that tree's classification performance is given by this formula. But you want to actually cut down the tree and see if there is a better tree that will predict and explain better as well, as I told about the explanatory purpose also. You try to prune the tree to assess its performance, and in order to do that you apply an alpha. So what happens when you apply an alpha? There is another term added, okay, here. Okay. So essentially the tree algorithm, the pruning algorithm then tries to prune or cut off certain branches and recompute the classification error. For example, the tree would first cut what is the first leaf node, then the leaf node T4. So what it will do, it will not have this split, okay. It will not have the split at T2, T4 is not formed, okay. And that may not be the point to start, okay. It should start with T6 and T7. If there is no T2 split, then T6 and T7 is gone, right. So let us start from here. T6, T7 are leaf nodes, split at T5, and what it will do is it will cut this, okay. T5 is not split, and then so your number of leaf nodes have come down, right, it has reduced by 1. So what is done is it will calculate the error. Okay. It will calculate the total classification error without a split at T5. With split at T5, you know the value of error, which is E1. Without the split, suppose your error is E2. Okay. The pruning algorithm will retain a split at T5 only if E1 is less than E2. Okay, or when you split at T5, the error is less, okay, error is reduced. So therefore the split must exist, but by removing the split, if you have increased the performance of the tree by reducing the prediction error or classification error, then do not split, okay, you remove the split. So this iteration or these steps continue for every leaf node, and then you prune or not prune based on the classification error, and that is the procedure or that is the algorithm for post pruning using CCP alpha. Okay. There is also an element of complexity here, cost complexity pruning, because larger trees are more costly in terms of prediction, okay, because you have more computation involved. Okay. So by pruning the tree, you are also reducing the complexity of the tree. Okay. So these are some of the essential lessons for understanding tree pruning. Okay. Pre-pruning, which is not recommended, post pruning using CCP alpha, which is one of the widely used techniques for tree pruning. Okay, to summarize, decision trees are widely used, they are good, they work with different types of variables. You can actually mix categorical data, continuous valued data, all in your list of attributes. Decision trees work well, and this is developed by the algorithmic community. It is not statistical, so therefore there is no particular assumption of distribution, but it works well with large data sets. Okay, and it is interpretable given that the tree size is controlled or pruned well, and generally the prediction performance of trees are good. Okay, now there is also a problem with the normal decision trees like the CART algorithm, which I indicated some time back. So, prediction performance could vary based on the training partition and the dominant predictor variable. There is a dominant predictor variable, the decision tree performance will be very much dependent on that variable. Okay, and also this is a problem which we already discussed using during the cross validation discussion. Okay, but in order to improve the performance of decision trees, okay, tree is standalone. Okay, it is one tree. Okay, it is one tree. Okay, but in order to improve the performance of decision trees, scholars developed alternate approaches, of course fundamentally based on the concept of tree. Okay, but when you have too many trees, okay, when you build a number of trees, okay, it can actually become a forest. Okay, okay, so create a forest of trees, okay, is the idea behind the improvement in decision trees to make them more better performing algorithms. Okay, and that is what we are going to discuss in the next slide, bagging, boosting, random forest, etc. Okay. So, the idea is to improve the classifier performance. Decision trees stand alone, a tree algorithm and a classifier developed by a tree algorithms has certain performance. Okay, but in order to improve the performance of those trees, in literature you have different alternate techniques. Okay, and those techniques as a whole, as I said, is known as ensemble methods. Okay, ensemble. Okay, ensemble is a collection. Okay, a collection of diverse elements. Okay, a bouquet with a number of flowers and leaves and all that, you know, it looks beautiful. Okay, but they are diverse in nature. Okay, if it's a one type of, if there is a garden with one type of flower alone, it's not that attractive. Okay, but when you add diversity, okay, it looks better. But here of course my example is very weak because it's not for look that you do it, but it's for prediction performance. Okay, okay, so what is the idea? Okay, as I said, as Bremen, who actually proposed this alternate techniques, he says instead of having a tree, have a forest. Okay, and what is that basic idea? That is what is shown in the particular diagram here. The idea is you have only one data set which is D, but using the same D data set, if you find a method to create T number of trees, not just one tree. Okay, each one stands for a tree. C1 is a tree, C2 is a tree and CT is a tree. You create T number of trees or create a forest. Okay, and then make each tree predict, and therefore you say you have a new data sample which is the test data. So, you in the first phase you built the trees or decision tree induction, okay, or training stage. Now you have test data, you make the trees predict, okay, and combine the predictions or classifications of each tree to arrive at a final prediction. Or in other words, don't go by the prediction of one tree alone, combine it using some logic, okay, and then use that combined prediction as the final prediction. So, your reliance on one tree alone can lead to bias or error. Okay. So, therefore, you build many trees and make each tree predict and then combine their predictions. It is easy to say that you create T number of trees, but if all the T trees are similar, developed from the same data, those trees will be very similar and their predictions will also be similar, and therefore is it worth going for it? But that is not the way ensemble methods work. Okay, you actually make each tree different. We will talk about it. So let me use an example here. Okay, the idea here is, as I said, instead of relying on one tree alone, go by the predictions of many trees or many classifiers. Okay, it's like if somebody has a serious sickness and one doctor recommends a surgery. Okay, what do you do? Well, the doctor is an expert, okay, and he has diagnosed and he has a recommendation. Okay, well, if it is a serious medical intervention, we all generally go for one or two more experts, and you actually have a diagnosis done with 2 or 3 experts more and take their opinion, right? And then you look at the opinion that is emerging as the dominant opinion, okay, and you go by that. This particular approach is similar to that. Okay, you don't rely on one expert or one classifier, but build or consult many experts in making the final prediction. Okay, that is an example. Now, the important question is how to build number of trees different from each other. Okay, when you go for expert consultations, you may be consulting one doctor who has a particular set of qualifications and experience in the field. You also look at you may not go to the same hospital or someone with the same track record. You want to go to someone who has, of course, qualifications and also has worked say in different contexts, okay, but in the same field, okay, for addressing the same kind of disease, but you want some diversity there. Okay, only then it is diversity that actually makes the outcome more valuable. Okay, and it is that diversity that you need to build into the making of the trees. Okay, and in order to do that, okay, one approach which is bagging and also in boosting, okay, how you build diverse trees is the same. Okay, you actually work on the data set, okay, and generate data sets that are different from each other. Instead of using the same data set, you create subsamples from the same data and use that different subsamples from the original data set to create the different decision trees. Okay, and having created the decision trees differently, you in bagging, which is one algorithm based on similar to tree algorithm, but it builds number of trees. Okay, so in that is an ensemble method. Okay, in the ensemble method which uses bagging, you build the trees using different subsamples of the data set, and then you just average the prediction. Okay, some kind of average prediction is used to arrive at the final prediction. That is bagging. But in boosting, you don't go by a simple average, but you weigh it. Okay, use weighted votes of each tree. So therefore, each tree gets a weight. Okay, this is weight 1, weight 2 and weight T. What is the basis for the weight? The basis for the weight is the prediction accuracy, the accuracy of the model. Okay, if C1's performance is better than C2's performance, then C1 gets a higher weight than C2. Okay, so each tree gets a weight based on its performance, and weighted sum of the predictions of the different classifiers is used or the weighted average is used to make the final prediction. Okay. That is about boosting. So, bagging and boosting uses subsamples to build the trees, and then one uses a simple average, other uses a weighted average. Then the third class of ensemble methods actually is slightly different from the two. It is similar in the sense that it uses multiple subsamples to generate the trees, but it further add one more source of randomness into building the trees to make the trees more diverse. And empirically, random forests have been found to perform better than other types of ensemble methods. Okay. This is a general observation. So, so let me explain these concepts further using certain slides that follow. First of all, okay, bootstrapping. Bootstrapping is an idea to generate multiple subsamples from an original sample data set. Okay, you have an original data set which is shown here. Okay, that is your training sample. Okay, the data set D in our prior discussion. Okay, now what is done in bootstrapping is that the various records here are Z1, Z2 to Zn. Okay, you randomly pick one record, one tuple, okay, or one object from this data set, okay, and place it here. Okay, you picked some Zk here. Okay, that is your first data point for a new set of data that you are building, which is Z1, capital Z1, and then you put that Zk back into the data set. That is called resampling with substitution. Okay, in bootstrapping, resampling with substitution. You pick a random data point and move it, don't move it, put it in a different data set that you are creating, but then replace it, and then again pick another data point randomly from the original data set, place it in the new data set that you are creating, that is set P, some other value, again put this value back. Okay, it is replaced. Okay, it is resampling with substitution. In this, continue this till you can specify a size for your new data set. Suppose you specify it as n. Okay, so n iterations. In n iterations, you will randomly take n number of data from the original data and create a new data set. And there is a theory behind bootstrapping, that the new data set that you formed by randomly selecting data points from the original data set will have the properties of the original data set. Okay, and this is a bootstrapped data set. Okay, and similarly you can create another bootstrapped data set and any number of bootstrapped data sets. So in the previous slide when I showed you that you have only one data set D, how do you create T number of trees? You create T number of bootstrapped data sets, and those data sets will be used for building T number of trees, and that is the method. Okay, so originally in the case of bagging and boosting, you are actually, and in also random forest, you actually use bootstrap data set for building the trees. Okay, now as we have seen in the case of bagging and boosting, the procedure is the same. The only difference between bagging and boosting is that in bagging you use the simple average, in boosting you take the weighted average and weight depending on the performance of each tree. Okay, and that is understood now. Now in random forest, there is a subtle difference. Okay, as compared to bagging and boosting, there is a difference. Okay, in random forest, till you build the tree, the method for building the tree up till this point is the same. That is, you have 1, 2, T number of subsamples that you created from the original data set, okay, using bootstrapping. That is the same. So, you have data sets and you are going to apply a random forest tree algorithm. What the random forest tree algorithm would do is that instead of making all the attributes A, suppose there are P number of attributes, okay, A, B, C to P, okay. P is the set of attributes or the attribute list, okay. Now, okay, since in the slide it is showing M, I will actually, instead of P, I will use M here, okay, M number of attributes, or the number is M, okay. Now, again that will not be very accurate because the small m is used to represent a subset, okay, but you understand what I am trying to say, okay. If it is a tree algorithm, it is a general tree algorithm. When a node has to split into two, the search algorithm will evaluate a split criteria based on all the attributes, right. It will evaluate the split criteria based on the purity that is given by each attribute, and then it will choose the right attribute A, B, C or M, whichever gives the best purity, correct, we discussed that already. But that is applicable to a cart algorithm, to bagging, boosting, etc. Okay, that is the method. But when it comes to random forest, at each node, a subset of the attributes, a subset of the attribute is made available instead of the whole list of attributes. At each node, when the node has to split, it is not the M, capital M number, but it is a small m, a value which is a number which is less than the number of attributes. A smaller subset of the number of attributes is made available at each node. What is the idea here? Essentially, each tree becomes different, okay. You decorrelate the trees further, okay, or the diversity among the trees will be much more when you use a approach like this, where the node has a subset of attributes that is used to split, okay. So, therefore, when you use these trees which are more decorrelated from each other, the performance, the overall performance of the tree or the algorithm is found to be better than other trees, okay. There is empirical evidence for the performance of random forest, okay. Random forest here meaning randomly selected subset of features or subset of attributes for splitting the nodes, and that is why it is called random forest, okay. Of course, Leo Breeman could be called the father of decision trees, who has extensively contributed to the tree algorithms, including that of the random forest, okay. So, in the next class, we will not be using cart in R. You can actually use cart and other algorithms which we just discussed in R or in Python, but instead of R, I will be using Python to explain to you how to implement these algorithms to address a given problem, okay. And that will be our next step, okay. So, we have learned certain fundamental concepts or we have got an overview of how decision trees and further improvement on decision tree, which are the ensemble methods, okay, they work, and now we are going to apply them, okay. So, that is our next attempt, okay. Thank you very much for listening, and wish you all the best in learning and further exploring classification algorithms. Thank you.